experiments to refer to. Now, we haven't fully fleshed out all of general relativity yet, but there's one experimental fact that I can use to show you that spacetime must be curved, just based on what we've seen in this series of episodes so far. It's a cool argument originally presented over 50 years ago by physicist Alfred Schild, and it goes like this. Fire a laser pulse from the ground floor of a building up to a photon detector on the roof. Now wait 5 seconds, and then do it again. On a flat spacetime diagram, the world lines of those photons should be parallel and congruent. Without making any assumptions about how gravity affects light, that would be true even if it turned out that gravity slowed photons down and bent their world lines, since both photons would be affected identically. Now, if spacetime is flat, then clocks on the ground and on the roof should run at the same rate. They're both stationary. Thus, the vertical lines at the ends of the photon world lines should also be parallel and congruent. But if you actually do this experiment, you find that photons arrive on the roof slightly more than 5 seconds apart. The excess time is less than a nanosecond, but any discrepancy means that clocks are running at different rates, in which case the opposite sides of this parallelogram aren't congruent. And that's geometrically impossible if spacetime is flat. Thus, the very existence of gravitational time dilation, regardless of its degree, requires that spacetime be curved, and that means game over for Newton. In fact, to the extent that we can speak about space and time separately at all, most of the everyday effects on Earth that Newton would attribute to gravity are due to curvature in time. The 3D space around Earth is almost exactly Euclidean. Those pictures that you see of Earth deforming a grid the way a bowling ball deforms a rubber sheet, or even the pictures we sometimes use on this show, they all suggest spatial curvature only, so they're somewhat misleading. Remember,